Okay, so in covalent bonds, atoms share electrons, and there are several interactions. There are attractions between the electrons and the nucleus. There's repulsion between electrons, and there's repulsion.
Now we can study these using a graph like this, where we put potential energy on one side and then we put internuclear distance between the two. So let's start with hydrogen, or H2. If we have two hydrogen atoms together, as we move them really close together, they're going to want to push on each other. In other words, there's going to be repulsion. As we move them farther apart, eventually they're going to get into an area where there's this sweet spot between attraction, and then as we move them really far apart, they're going to be so far apart that Coulomb's law says there's not going to be a great enough force to pull them together. And so if we're below this line, it's attraction, but what we'll find is when we have the perfect distance apart, we're going to reach what is the bond energy and the bond length of those two atoms. In other words, bond length is going to be how far generally hydrogen atoms are going to stay apart, and bond energy is how much energy would we have to put in to actually break that hydrogen apart. So this graph is incredibly important.
Now, electrons are not always equally shared. As you know, if I take fluorine and hydrogen and I make hydrogen fluoride, we know that the fluorine is more electronegative than the hydrogen. So the fluorine is going to pull harder on that pair of electrons than the hydrogen will. And what we say forms is a dipole. And we draw the dipole like this. We would draw an arrow. And the more negative side would have the head of the arrow. And we'd put a little plus at the end. It's almost like this is the more positive side. It becomes like a little plus sign. So this, we would indicate a dipole here. There's no dipole here in the fluorine. They share equally. Okay? So this is going to become a polar molecule. There's more electron density here where the fluorine is because it's going to pull more on those electrons. And it's all governed by electronegativity, right? So if you remember, the most electronegative element is fluorine. It's a very high Zeph. As I go across, I'm increasing the effective nuclear charge. At the same time, I'm adding electrons. Okay? And as I go down a group, I'm getting more shielding of that Zeph, or that electron, or that nuclear pull, as I add more shells. So remember those trends, because the higher the electronegativity, the more that atom is going to pull on the electrons, therefore making it more polar. Okay, so it's the difference in electronegativity that determines, in a bond, that determines whether or not a bond is polar. So as you remember, from left to right, electronegativity goes up, and from the bottom to the top it goes up. So if you think about fluorine as the high, it goes down from there both ways. So when atoms share electrons unequally, we call that a bond dipole. One's more positive, one's more negative. There's some distance between them. There's actually a way to calculate what's called a dipole moment. It's got a value of U, and it's produced by unequal charges separated by distance. Now we're not going to actually calculate these, but you do need to be able to compare the differences in the dipole moments based on differences in electronegativity. So the greater the difference in electronegativity, as you can see, the highest electronegativity has the highest dipole moment. Okay, so the greater this is, right? And these would be, you could draw these as a shorter arrow than you would here. Okay. Now what you'll see is higher electronegativity difference, higher dipole moment, and shorter bond length, and that's because those electrons are being pulled tighter in, making the bond shorter. So the lower the electronegativity difference, the larger the bond, the further away the electrons or the two nuclei in the atoms are. Okay, so all these three things go together, and you need to understand their relationships. Alright, so in order to determine which bond is more polar, we need to look at the table of electronegativities. In general, when you get asked questions on the AP exam, you'll need to use the trends. But if you wanted to compare exact differences, you can use a table of electronegativities. Okay, so if I look at boron chloride versus carbon chloride, I have boron is 2, has a value of 2. Chlorine has a value of 3, so the difference here is 1. Carbon has a value of 2.5. Chlorine has a value of 3. This difference is 0.5. So the greater difference is boron and chlorine. So that's going to be more polar. If I look at PF versus PCl, so here's F, here's Cl, here's P. It's going to be obvious that it's going to be F because it's further away from the P than the Cl is. But if I actually put numbers to it, P would be 2.2 for both. Whoops. F is 4. Chlorine is 3. So this is going to be 1.8, or let me see. Was that a 2.2? 1.8? This is going to be 0.8. Okay. So the PF is going to be more polar.